How can I justify hating on second and third normal forms the way that I do? This video will lay out the reasoning and provide you a vastly superior alternative. Welcome to this video on database normalization. My name is Kevin Fiesel, and I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, we learned about what first normal form is, as well as what it isn't. Now we're going to build on top of first normal form and cover one of the two most important normal forms. You can probably hear the excitement in my voice about being here. The judge says that I need to do at least 5 more of these videos before my community service is complete. At least this topic's a good one. Boyce-Codd Normal Form. You know a normal form is good when people are willing to name it after themselves. Boyce-Codd Normal Form is one of the two most important normal forms because it prevents a variety of data anomalies, update anomalies, some types of redundant data, and missing data. Let's say we have some data. This relation represents booking dates for artists to record albums in our recording studios, and each recording studio has a manager associated with it. The relation is in first normal form, but it is susceptible to the 3 types of data anomaly we discussed. Let's suppose that Lindsay takes over as the manager of Studio A, so we update the data. The problem is, however, that our update statement missed a row, which still has Marie as the manager. That's a bit of an oopsie and could cause end users not to trust our data, because it's wrong. While we're fixing that issue, we get a call from one of our bands that they won't make it today. That's fine, we'll just have the other band who was scheduled to record stick around longer and record more tracks. Except now we have a problem. This leads to a duplicate tuple, which violates first normal form, so that's a no-go. Also, why isn't anybody booking Studio C? Wait, you didn't know about Studio C? Sometimes we see, special approaches to solving this problem, like inserting obviously fake data just so we can see the existence of our third studio. If you have to insert fake data into a table to have necessary data elements show up, you should take that design back to the drawing board. So those are the 3 data problems that we can fix with Boyce-Codd Normal Form. But what is BCNF? Well, here's the formal definition of it. All functional dependencies have superkey determinants. It's just 6 words, so easy enough. I guess I have to explain those words. Okay, let's start with superkeys. A superkey is a key that wears its underwear outside of its pants. It is also a combination of attributes which guarantees uniqueness for each tuple in a relation, but is not necessarily the most parsimonious unique combination. Suppose we have a key of recording date and artist. Each combination is guaranteed to be unique for this relvar. In that case, recording date alone is called a subkey. It is a part of the key, but not sufficient to be a key on its own. The combination of recording date, artist, and studio is a superkey. We know trivially that this is unique because we already know that the combination of recording date and artist is unique, and we can't remove that property of uniqueness by adding new attributes. That's a superkey. As a quick note, a superkey is also a key, so recording date and artist is also an example of a superkey because superkey is greater than or equal to the number of attributes necessary to guarantee uniqueness. Now let's talk about the concept of functional dependencies. To do this, let's suppose that we have an additional attribute called sound engineer. Further, let's suppose that the value of sound engineer depends on 2 inputs, studio and producer. When Janice is the producer at Studio A, she has Sam working as her sound engineer. When Randy is the producer at Studio B, she has Edgar as her sound engineer. when Tamika is the producer at Studio C. She has Sam as her sound engineer. From this table, we know that when studio is A and producer is Janice, then sound engineer is Sam. In other words, studio and producer determine sound engineer. In mathematical terms, we write it in this format, where the determinant is on the left-hand side, and if we have multiple attributes in the determinant, we wrap them in parentheses. Then, we have a right-facing arrow and the attribute we are determining. This entire thing is called a functional dependency. It's important to note that functional dependencies only go one way. We have studio and producer determining sound engineer. So studio A and producer Janice necessarily imply that Sam will be the sound engineer. But having Sam as the sound engineer does not determine who the producer is or which studio we are using. In this case, we also know that Sam pulls sound engineering duties for Tamika in Studio C. Now we get to what I think is the important question. How in the world do we actually figure out what these functional dependencies are? In the world of academia, functional dependencies come down to us like manna from heaven. It's a pretty neat trick if you can pull it off. But in the business world, we have to fight for our functional dependencies. There are two techniques which can work reasonably well to suss out functional dependencies. The first is to ask an expert. Discuss the business rules and find out what your subject matter experts know. The primary downside to this is that you would have to have a conversation with another human being, which is pretty awkward, I know, but it's important to do this. The second technique is to review existing data you have and see where you can find columns whose values always match up in a certain way. Always is the key word here. Functional dependencies either hold or do not hold. It cannot be a sometimes thing with them. Here are a few ideas which might help. First, look for common prefixes like user ID or username. Those prefixes often give it away that there's a functional dependency in there somewhere. Second, there may be cases where we can imagine an attribute belonging to an object, like how a password associates with a login. Third, look for equivalencies and mathematical formulas in your data. An example of this might include subtotal, tax, and total, where subtotal and tax determine the total. All that said, let's go back to our definition of Boyce-Codd Normal Form. All functional dependencies have superkey determinants. We know that a superkey is a key, and maybe more. A functional dependency is a strict relationship between attributes, and a determinant is the set of inputs for a given functional dependency. In other words, if we have a functional dependency in our relvar, the inputs for that functional dependency, that is, the determinant, must include all attributes in a unique key for that relvar. If we satisfy this condition, our relvar is in Boyce-Codd Normal Form and is guaranteed to suffer from none of the anomalies we've described. Now that we know what Boyce-Codd Normal Form is, let's see an example of how we can solve for it. We're going to start with a single large relvar containing all of the attributes we care about. In this case, we are going to work with a digital marketing campaign, and the combination of attributes which makes a tuple unique here is the combination of campaign ID and audience target ID. This forms a candidate key, one of the collection of unique keys for a relvar. In this case, we only have one candidate key, but in other relvars, we may have multiple candidate keys. Next, I want to sort out all of the functional dependencies. Through brutal interrogation of subject matter experts, relentless detective work in the existing dataset, and a bit of domain knowledge I've secreted away just for this occasion, I have come up with 4 functional dependencies. The first functional dependency is that campaign ID determines the campaign name, the campaign owner name, the agency ID, the max budget, and the minimum bid. For those people not in the know about digital marketing, a campaign is a series of advertisements we are going to sponsor. We're going to tell an advertising agency that they will have some amount of money to advertise our albums on search engines and the like. We are, for each advertisement in the campaign, willing to pay a certain amount of money to get our advertisement shoved in the face of a viewer. That's our minimum bid. And our campaign owner is the person on our side who will work with the ad agency and make sure everything is going well. Next up, we have agency ID, which determines the agency name and the take rate. The take rate is the percentage of sales that the agency will collect in the event that someone buys one of our albums as a result of viewing an advertisement. In our scenario, different agencies have different take rates, but we negotiate one constant take rate for the agency, regardless of how many campaigns they're running or how important those campaigns are. Our next functional dependency derives from audience target ID, and the audience target ID determines the targeted age range and genre preference. The idea here is that we might want to target specific groups of people for certain albums. For example, if we have a new album coming out from a band which typically sells well for people aged 18 to 30 who like Finnish death metal, we might have an audience target for that group of people. The combination of campaign ID and audience target ID determines our last attribute, audience bid modifier. Our minimum bid for an advertisement might be 10 cents per click, but if there's a good match between the album we are advertising and the target audience, we might be willing to say that we want to spend 50 cents or even $1 per click to show that advertisement to that person, because that person is much more likely to buy this particular album. Now that we know what all of the attributes mean and what our functional dependencies are, we can move to the next step of the problem. In this step, we ask the question, are all determinants candidate keys? The answer to this is obviously no. The only determinant, which is a super key, is the last one on the list, which is campaign ID and audience target ID. We have campaign ID and audience target ID separately as determinants in the list, but those form sub-keys, whereas we need super keys. Therefore, those don't count. And agency ID isn't part of any candidate key, so it's right out. What are we supposed to do at this point? Well, let's take a step back and introduce Heath's theorem. Suppose we have a rel var R, and it has some collection of components, which, for the sake of being generic, I'll say are X, Y, and Z. Furthermore, let's also postulate that there is a functional dependency where X functionally determines Y. If all of this holds true, we can break out rel var R into two rel vars, where the first one contains X and Y, and the second contains X and Z. We can do this without loss, meaning that later we can combine the two rel vars back together using a join operation on X and get back the exact same tuples as we had before. No more, no fewer, and no different. The neat thing about this is X, Y, and Z are generic terms. Y and Z here could represent half a dozen attributes apiece, and the math still works exactly the same way. Now let's see how this applies. If we answered no to the prior step, which, by the way, we did, then what we want to do is take a non-candidate key determinant and break it out into its own rel var, following Heath's theorem. I'm going to start with agency ID, which is my X. The Y is the stuff which agency ID functionally determines, agency name and take rate. And Z is everything else. We'll create one rel var called agency, which includes the agency ID, the agency name, and the take rate. Then, our other DM campaign rel var will keep agency ID on as a foreign key, but we'll remove agency name and take rate. Now that we've done this, we repeat the steps. Are all rel vars in Boyce-Codd Normal Form? No, because there are still functional dependencies in at least one rel var which are not candidate keys. So let's strip out campaign next. I'll take everything determined by the campaign ID out and put it into its own separate relvar. We can see that the DM campaign relvar is getting smaller and smaller as we do this, and also that the agency ID foreign key went over into the campaign relvar. Once again, we ask the question, are we done here? Well, we have 2 functional dependencies remaining, one of which uses audience target ID alone, so no, this isn't good enough. We will need, once again, to break that out into its own relvar, taking with it target age range and target genre preference. By the time we are done with this, we now have the following data model, constituting 4 relvars. And along the way, I took the opportunity to rename the DM campaign mega relvar into something which is more meaningful given the data that remains. This relvar actually represents a campaign target, not a campaign. This is why I consider Boyce-Codd Normal Form to be so important. It gets rid of a variety of data problems, and there is a clean formula helping us understand how to get there. If you have data in Boyce-Codd Normal Form, you are in pretty good shape. But what's my beef with second and third normal forms? The short answer is that Boyce-Codd Normal Form subsumes second and third normal forms. If all relvars in my data model are in Boyce-Codd Normal Form, they are necessarily in second and third normal forms. But my relvars that are in second and third normal form are not guaranteed to be in Boyce-Codd Normal Form, specifically when I have multiple candidate keys. For this reason, I see absolutely no value in caring about second or third normal form, and I'll instead go straight from first to Boyce-Codd Normal Form. Class dismissed. And there you have it. Boyce-Codd Normal Form is one of the 2 most important normal forms. In the next video, we're going to take a look at the other S-tier normal form, 5th normal form. We'll have links and show notes in the description below. And until we see each other in the next video, take care.